Welcome to J&J's Retro and Repairs. Today I have with me this Commodore 64 that I purchased from eBay, knowing that it likely needed some repairs. So to prepare it ahead of time, I did some basic power on tests, hooked it up to video, powered it on, and noticed it wasn't working properly. However, we will have to dig deeper and find out what's truly wrong with this machine together. I'm trying to make this video in such a way that if you need to, you could repair the Commodore 64 at home as well. I will make this video as simple as possible and try to make it so that I use the fewest possible materials and resources. I'll provide links in the description below in case you want to do this repair yourself. Feel free to leave your comments in the sections below if you like my video. If you don't like my video, you can thumbs down. If you like it, thumbs up. I would like to give a special thank you to WM for providing the music for my video. And anytime that you hear an intermission, the video music comes from him. Now, let's get started and have a look at this machine. Here we are, and we're starting to record the repair of this Commodore 64. Now, I've had this Commodore 64 open already once before, so it's not the first time that I've opened it. So there are no screws in it right now. I did have a quick look inside to see if there is anything that I need to attend to, but let's have a look inside together. There we go. Let's take off the and not much to report there. Now, looking inside, you can see that RF shield is still there. That will be a problem for me. I need to get that off. But it is the paper shield, so that should be fairly easy to get off. And there is definitely a shield. You can see that there's definitely a shield right here. You can see the shielding is soldered onto the board still. And this is a 250 407, the classic 250 407 board. So nothing special to read about here. I'll bring this down a little closer so we can have a closer look. Have a closer look here. You can see that it is in fact a 250 407 board, if you can see that. I think you can see that on there. You'll notice that all these chips are soldered, with the exception of the SID chip, which I will pull out actually. The SID, I don't want to damage the SID, so let's pull that out first. I could do it with one of these possibly. And I can use the chip extractor to get it out the rest of the way. And that is the SID extracted, which is great. We'll check that SID later to see how it actually works out. So with the SID extracted, I would like to go deeper into this board, so it looks like Phillips screwdriver is what we're going to need. I'm just going to grab that. Before I do too much more, make sure I'm strapped up. You can quite clearly see that all of this, like all of the screws here are not tight, so I'm probably not the first person into this board. Quite likely won't be the last. My intention of this particular machine is to turn it into a ZIF64 if possible. I aim to replace all of the chips with, or at least most of the chips with ZIF sockets. So that basically, right now there's no sockets on this board at all, which actually is ideal for ZIF64 because the more sockets you have, the more sockets you have to pull out, and sockets are harder to desolder than chips. Now, on the flip side of that, anytime you desolder a chip, you risk damaging it. So it is possible that I may damage more in the process, but that's why I'll do it one chip at a time, so that if I do fix it first and get it working, then when I change one of the chips, I will know if I break the board again. So if you change a chip for a socket and it stops working, it limits the things you need to look at to know what needs to get changed. So these screws are awfully loose. This one in particular. So I'm going to guess that maybe these stands are not working. Maybe they're broken or non-existent, because this screw is not even coming up. Not releasing. So whenever you have screws that don't want to release, I try to get something underneath them to help wedge the screw up, and then the threading will probably be sufficient to get it out. You can use a leverage of any kind, even something as simple as like this, if it's not in the way, can help give leverage so that you can screw it out. This sometimes using a flat head screwdriver or anything at all that will give you a little bit of leverage to be able to pull out the screw. I'm going to guess the screw is not even in at all. Oh, it is. The mount gave way. There's no mount there, so I will just leave that as it is. Let me get this last screw out over here. Let's see if we have any more holding on. Oh, one more screw on the far corner between the ports. The screw in the bottom corner is not holding, so let's see if there's anything holding on. Nope. And these just trap heat and destroy your systems, so better off getting rid of them. And this thing here is just a death trap waiting to happen. This can fall down into your components and just short out and cause a really wonderful explosion on your motherboard, which is not something you want. So here it is, fully released. I will take the plastic away. I would think, yeah, I was right, detached and broken away, unfortunately. In fact, a few of these mounts have broken away. So for this one, there's not much that can be done. When I reassemble it, I will put those back in place. There are ways that you can actually reattach the mounts. They're not always ideal. They all have different ways of doing it. I'll probably end up using some kind of an epoxy or something to get it down there, get it nice and strong. I have one such epoxy present actually, which I may end up using. So that right here, JB Weld. Hopefully that one works and does exactly what I want it to do. So if we can, I can reassemble that back together again, put the screws back on. I'll make a separate video for how to fix a case, things like that. This video is purely repair. My aim here is to try and see what we can do to repair this board back to its normal state. But before I do that, what I can do here is show you what this board does when it is connected. So I have powered this up before. It had a few different modes that it went into when it powered up. They're all different. Let's see what we see. Now you can see there's crazy noise happening all over the screen. This can happen from multiple causes. It could be the VIC chip, it could be the PLA, it could even be the CPU, but less likely the CPU because it probably wouldn't make it this far if the CPU had failed entirely. It can still be the CPU if it's holding certain lines or data lines low and forcing them low, so it could cause artifacts like this. But I would say more likely this seems to be something along the lines of where it is seemingly just cycling through memory and doing everything. So it is most likely a logic chip or the PLA in this case. So the first thing we're going to have to do is fire up the desoldering iron. So I'm going to try and remove this PLA chip right here. This one seems to be, it's a 906114-01. And I have, in fact, a replacement, or a couple of replacements actually, 906114-01s. You can see them in the, right there. There's one there, and then there's another one right there. So one of those will likely work. First of all, we'll need to take this shield off. In order to desolder anything, you cannot desolder it while the metal shield is on. Interesting thing about this particular board I noticed was that one of the tabs was not soldered, and there's no evidence there of desoldering. It just was never ever soldered from factory. So that's an interesting thing. So let's get some desoldering going. All right, so the desoldering iron is warmed up. Now this particular one is more like a desoldering pump. This one you have to touch the solder and desolder it while you're pulling the tab up, but if you're trying to get the solder out, you only get to do one pump request, like that, and then you have to release it. You get one pump and then you have to release. So the tip works differently than the continuous pumps. This is like a single shot pump, more like a solder sucker, an electronic solder sucker than an electronic solder pump. So then it works a little bit differently, and so you have to kind of do it in sections. But it works really good for getting these tabs off. And then once you remove enough of the solder and there isn't as much contact anymore, then it should just automatically release the from the board. So getting the flat end of the screwdriver in there and slowly working my way along, and then slowly getting this desoldered one at a time until I get all of them. So I will do a quick sequence here where I do all of this. So I have a bit of a problem on this section. I may have to cut this part, only because it's between the two sockets. And if I put my desoldering iron in there, I'm definitely going to touch them. There's no question about that. There's not enough clearance. So, note to self, some of these are too cheap and do not last for very long. I think I may have used this about 3 times and it's now dead. So after my desoldering pump stopped working, I decided I'd pull out the solder wick and let's try this again with the solder wick and the soldering iron. The soldering iron can do most of the work fairly well. I have 2 kinds of desoldering wicks. I haven't actually tried these ones yet, so it'll be interesting to see how they work out. So it would be nice to find out exactly how these particular solder wicks work out in the end. I'm not sure because I purchased both of them from AliExpress, which is questionable, but I guess we'll see exactly how well they work. So let's get started. So as I was saying, going to say earlier, was that we can use the desoldering braid. It's slower. It takes a lot longer to do. But once you wick away all of the solder from the actual solder point, once it's all wicked away, then you can actually pry up the tabs one after another with a little bit of heat from the soldering iron. It's not a quick process. It's actually a lot slower than if you have a desoldering iron, but it still works. That being said, I will continue at this for the last 2 tabs, then I'll clip away the final 2 tabs, and then we should be done. Too bad that I had to bend this aluminum. I didn't really want to bend this aluminum to do this, but I did get it off, and it's in decent shape still. I will have to clean up this spot, but I did get it off the bottom without too much damage, and I did actually preserve it. Although I don't think it'll matter too much, since this board will be used for ZIF64 and I'll probably want always to have access to the bottom. So, more than likely this is not going to matter, and I won't even keep this, or I'll keep it to the side for a different one that may be missing one. I won't be keeping it for this one. There is no value in these RF shields nowadays. I mean, there might be value in this cardboard if you're going to put that bottom RF shield in, though, because that cardboard protects the circuit on the bottom when you want to put the shield on so that it doesn't short out all of these components. How well that works, hard to say, but it does generally keep or prevent shorting anyway, for the most part. So it's been a couple of weeks now, and I actually went ahead and purchased a Hakko Desoldering iron. So that will finally be what I use to actually do the final desoldering. So I think what we want to do here is we want to make sure that we do the desoldering properly, and the previous iron that I had failed quite miserably. This one. But you get what you pay for, right? This one was cheap. I'm pretty sure it wasn't more than $80. Maybe it was like 50 or 60 actually. So get what you pay for. Maybe in a future video I'll do a repair video on this device to repair it to work again. I found that on ground planes this worked very well, probably better than the Hakko. So we'll see if I can get that working again. In the meantime, what we're going to do is desolder this board. Now we can inspect our work and see exactly what it looks like. Looks like I missed a couple pins, so I will continue desoldering. Something else that you can do is you can add some solder if it doesn't seem to be coming off. So add a little solder to the pin that you need to desolder, and that can help to contact with the existing solder. In case the solder is getting a little bit corroded and needs a little bit more solder, now we need to test and see if the chip is ready to be leveraged. So we need the hot air, I mean. Next I think I will do the hot air, and with the hot air you can use it to heat up around the chip. So, pins. The first pin on the top left and the fourth pin on the top left and the second pin here are all giving me trouble. I will continue desoldering these pins. I think I'm going to need to add some solder. Let's see which one is resisting me. Which pin is resisting? That one's let go. This one is still holding. That is one troublemaking pin. Well, I'll grab it and let's fire this up again. There we go. Oh, there. Oh, dropped. Dropped it like a pro. There we go. I will put this off to the side. I suspect that's a bad chip, but we'll see. It seemed like a pretty substantial win for us to get this far. But we have another problem. You see, I plan to put this particular socket in here. One of the issues with that, of course, is you need to get all these pins down and you need to fit it in such a way that it fits onto the board. And you can see my problem here. I have one capacitor sitting right here. That capacitor is not able to be moved easily, and this particular socket needs to go down in such a way that it has overlap, where you could put one of these sockets in easily enough, one of the regular sockets, but if you're using a ZIF socket, you can see that compared to this socket, it has a significant overhang on both sides. You can get smart about how you put this in, whether you want to put it in this way or this way. If you put it in this way, you do have more room, but then you also risk this, when this goes down, it interfering with the socket below. So you do have to make a wise judgment about where the socket goes. In my particular case, it's safest if I can get it this way. But I also have another problem here, where the DIN connector might get in the way of this. Now, that might be easier. I can easily bend this post a little bit out of the way so that it clears the DIN. But that'll be some experimentation to get that working. I'm going to figure out exactly how this is going to fit. So, after careful inspection, I was able to determine that the capacitor that is right here will need to get removed. There's no way around that. It will clear everywhere else, it just won't clear that capacitor. There's a few ways that you can fix that problem. You can either move the capacitor to the bottom of the board, or you can extend the leads of the capacitor and make it just a little bit longer lead so that it can be moved just closer to the DIN connector or to the side. Either way, you will need to move that particular capacitor to put in a socket of this particular type. So there may be other sockets that don't have as large of a footprint, but I haven't seen very many. Most of the ZIF sockets are generally larger footprint. than standard sockets. So you will need to make adjustments on the board wherever necessary. So we'll continue, and I will desolder that capacitor. I believe it is sitting right here. I think the plan here for us will be to increase the length of the leads of this capacitor, put a little shrink wrap around the leads, and move it off to the side. Gives a little bit more room. The leads will be a little more flexible than the original capacitor leads, and it will give me the opportunity to move it back further so that the socket will fit. Once you have wired the length you need, then you can tin it with the soldering iron, and then you can get what you need. So the point here is you want to make sure that you tin the ends with which will make it a lot easier for soldering later. Once you have it tinned, you can position it on the board where you need it to go. A little extra solder, and you can put that into the board. There. Clipping off any excess. Looks good. Now the point here is to make it so that you can fit the capacitor off to the side or elsewhere. So making sure to flatten it down to the board. You can test again. See how it fits. As long as all of the pins are making it far enough through, you're certain that you can solder it, you're good. And here is where we want to tack down some of the pins. So, let's see if we can get one of the pins tacked down. With 2 pins tacked, it's pretty solid in there then. A little bit of flex there. down the other corner just in case, because I suspect it needs a little bit more hold. All right, now it's solid in there. That's good. Now we reattach the capacitor. So we want to put this capacitor back onto the board because this capacitor will be needed as this is, I believe this is the bypass cap for that particular IC. Could be wrong, but I think it is. So we need this in place if we want everything to behave properly. What I want to do with this particular one, though, is I want to get just a little bit of shrink wrap over the leads and then solder these leads down to the extra wire that we added. And once the leads are soldered to the wire, then we'll bring the shrink wrap up and we'll use the hot air gun to tighten the shrink wrap. So I just need to go get some shrink wrap. I said shrink wrap. I actually meant shrink tubing. This particular thing allows me to choose the shrink tube size I'm looking for. So it's the smallest one in this case. 2 of them works for me. I've used these before. They're pretty good. Let's put this aside. So for the shrink tubing, I only need a certain amount, and I want this whole thing to be pretty stiff once it's finished. So normally you'd only need shrink tube over the solder point. I'm actually going to put a little bit more than that, just because I want it to go a little bit deeper onto the, onto the actual capacitor and the wire. This happens to be stranded flex wire, so I want to reduce the flexibility of the wire, and to do that, I'll need more of this. So I'll need about that much. Now that might be a little bit too much actually, now that I'm looking at it. I want enough so that the wire actually protrudes well enough so that I don't touch the shrink tube while I'm soldering. That's definitely not something I want to happen. And that means I have to cut it a little bit shorter. Let's see how that goes. We'll see how long that is. I want the shrink tube to fit down over the wire so that it falls to the bottom and is not, yeah, there we go. So you see there's a little bit of the insulation from the actual wire showing up. That's exactly what I want. That's exactly how I want it to show up. So and I solder here, pull the shrink tube up, and then heat it up. Now this will give me a short period of time when I can probably bend the wire into the shape I want it to be. I might just push it down near the other capacitors. I don't know exactly what I want to do yet, because I know for a fact that I also want to put another 40 pin here for the actual 6510 CPU. So I'll need a 40 pin ZIF socket here. So I don't want to move the capacitor in a place where it will actually get in the way of the new ZIF for the CPU. I probably won't do that in this video. I'll do it in a different video. This one is just, let's fix this system and make it work. First thing you want to do is add a little extra tin to the wire. Then holding on to the capacitor gently, stressing gently, we want to touch these wires together and get the tinning part to coincide and just hold on to it. I actually have a wire soldering station. I don't know why I didn't use it. My mistake, I guess. Now we can add some more solder to it. Not pretty, but it works. Now we need to check for continuity. So, with the multimeter set into continuity mode, that's good enough. We just want to make sure that the leads of the capacitor reach the bottom of the actual board. So we just need to touch this. Make sure it reaches the bottom here. There we go. Let's check the other side. There. Definitely contact. It's a little hard to get access to the wires because they're so buried in there. So for the capacitor for now, I think I'm going to push it off to the side. We'll just leave it there. This, we need to tack down the rest of the way and solder that down. Alright, I think we can call that. That's good. Guess the question here is now, should we just test a new chip in the socket and see how that works? I'm going to go for broke and try it out. So let's have a look and see how it works. Important thing here is to make sure that the notch is facing towards the video cable, the same direction as all the other chips here, and you can tell that the notch is right there. And I can put this down, and that should be nice and solid. Let's see what we get this time. And it works. It just works. Amazing. Like, we're now at the basic prompt right now. We could start doing something. That doesn't mean that it's 100% working, but you notice I only replaced the PLA and it all worked. I will include links below to show the reason why I knew that there was a PLA, even though I hadn't tested that PLA at all. I took it out of the board, but that's all I did. I didn't actually test the PLA to know if it was good or not. But I did recognize the video behavior. Sometimes it would be a black screen. Sometimes it would be that strange cycling video screen. But quite commonly, that is a PLA. Not guaranteed. There are other things that can cause that if some of the logic chips are wrong. But almost certainly it's a PLA that's failed. And this particular model board and this particular chip year, I'm not sure if you can see that in there. Anyway, this particular model year is 1983. So all of the boards between 1983 and 1984, most of those 2 years are pretty suspect for the PLA. So if you see that kind of a strange pattern on the screen for those model year bread bin boards, then the PLA is often suspect. Different problems exist on the 64C. It's usually RAM in that case, or one of the logic chips that had failed. The other thing to look out for is MOS logic chips. Now, if I saw MOS logic chips on this board, I would be very suspect of them, but I think the ones on this board are all Texas Instruments. Those are really reliable in comparison. And I haven't seen any MT RAM chips here, so that's another good thing. So MT RAM is another risk and suspect item. But usually with RAM failures, you don't end up with issues of this particular kind. Now, to be absolutely certain, I'm now going to run the entire diagnostics on this system. There it is. That's the diagnostic. You'll notice in this diagnostic that the two counters at the bottom are going up. That tests the real-time clock in the CIA chips, which means that both the CIAs are actually working for the most part for that test. You'll see a bunch of bad here, but that's only because I haven't put the loopback tests on. So that's, of course, going to fail. Next, we need to put the SID chip back in and see if it's good. Better check the pins. ready for testing. Make sure it's in the right way, make sure the pins are all right. The one thing about the SID chip is if you put it in wrong, anything at all offset, many of the other chips would survive because they can handle 5 volts on all the pins. The SID chip, on the other hand, has 12 volts on one of the pins, and so it would not survive offset or turned around. It would burn out the input lines. And let's see if we get any sound. I did not hear anything. I'll let it run a second time. But I'm going to suspect the SID is bad. I'll bring out the full harness to test to see, but I'm pretty sure that the SID is bad. That's disappointing. But before I give up, I think I will take out the deoxit and test the deoxit on the socket. Yeah, I'm not hearing anything. No sound whatsoever. Alright. I guess we will not have a working SID today. That is highly disappointing. I will try one more thing. I will take it back out of the socket and try to deoxit this socket and see if that will help in any way. Sometimes that revives it. The socket does seem a little bit difficult. So it could be just that the socket is needing a little bit of attention, because it is quite difficult to get that chip in and out. Next on the list of things, time to get the deoxit. Just a little bit in the socket. Make sure it's off. And try again. Make sure it's seated down nice and firm, and let's try it. Oh, yeah. That chip is getting nice and hot. I mean, they do tend to get hot, but I think maybe this one is toasted. I do have an arm SID. So let's take this chip out of the board. Quite suspect it's not working. And I'll just put it aside. Let's test the arm SID. So now with the arm SID, you hopefully should hear some sound. Oh, I am not... Oh, there is sound. Well, I guess because both chips are dead, they both deserve my special invisible ink X. And they go into my dead parts. And you may ask, invisible ink? Well, turns out you can see it, but only under UV light. I try to avoid marking up chips as much as possible. Using UV light ink makes it simpler. And I know those chips are bad. All I have to do is shine light on them and I know what the status is. Unfortunately, in the process, I broke my Armisid chip, which is really annoying. You can see there I broke one of the pins off. So I'm going to have to solder a pin on to fix that at some point. I won't be able to test anything more until I do. That is a sad state of affairs. I did not want to lose my Armisid, and I will have to fix that when I can. So, note to self, use a chip puller at all times if you can. In the case of this, I used my fingers and I tried to pull out. I pulled out wrong. I should have used a proper chip puller. I even have a proper chip puller right here. I could have used it, and yeah, that's on me. I made that mistake, and mistakes are to be made. When you do things like this, anytime that you work on a computer, you could fail. You could make a mistake somewhere. You're just going to make mistakes. That's just how things are. Now, I haven't validated this whole board. What I have validated is that the PLA is working. My socket install is working. The capacitor movement is working, although hard to validate that 100%, but I'm pretty sure that is working as well. And it also means that all I need to do now is package this board back up, put the keyboard on, and see if the keyboard works, because we have no idea if the keyboard's working at all. Now, that being said, I think that it would be wise to run a full diagnostic on this particular board. So after a bit of hard work and a little bit of fiddling, I was able to solder a pin back onto the Armisid and able to get it to work again. So now let's get the test harness out. All right, it's time to put the test harness into place. Make sure that everything's off. And the keyboard connector. Although this keyboard connector actually has 2 rows of pins, it only goes on either of the 2 sides. So it doesn't matter which of the 2 sides you put it on. The important part is that you put it on 1 row of pins and all the way across. The important thing, of course, is that if you notice there, you can see it, there's a gap pin right there. That gap pin needs to line up with the gap on the keyboard connector. There's the 2 joystick ports. There is the IEC loopback. User port and the cassette port. And that is all of the connectors in place. Now we should be ready to test for loopback. All the loopback is in place. We should be able to test for it now. All the lights on. That shows that there's power in all those ports now. That's a good sign. You want to see power on all of the ports. For this particular test harness, you want all the lights to light up. That's not a bad thing. For some of the test harnesses, the lights light up, like the cassette port light lights up and then turns off. It does look like there is a control port problem. And a keyboard loopback problem. Okay, I have taken all of the harness off, and now I'm going to put this back into its original case, which I have right behind me here, and I'll put the keyboard in and see how that works. Now, of course, we are missing some mounts here, so this won't go down quite flush. However, because it does have the here, it will actually help to hold it a bit. And that should be just fine like that. And the keyboard. So, I'll put down. All right, keyboard is in. Let's put in the power, video, and audio, and let's test it. See what we get. And we have the basic prompt, which is awesome. Let's test keyboard. Oh, wait. Keyboard is working. Oh, wait. Not all of it, though. Let's see here. Let's see which keys do and don't work. Enter is working. Okay, so let's see here. Oh, wait. Oh, look at that. Oh, wait, no. Oh, never mind. It's working. Oh, wait. Yeah, there is something wrong here. Do you see how it's... Oh, no, that's the right character. That is the right character. Slash... Down... Oh, shift is working. Left is working. Right is working. Okay, so I have cursor control. Commodore key. It looks at the Commodore keys working. Run stop. Well, let's see if I can do. Okay, it's running the program. That's a good sign. If it can run a whole program routine correctly. Now we're going to test the run stop. Now there is also something else the Commodore can do, and this will test the restore. Run stop restore will bring me to a blank screen, and that worked. So that means the run stop restore is working. Control key. That is working as well. So, and this is the back arrow key, and that is working. So I haven't tried the F function keys. I think the function keys, I don't know. They obviously the whole keyboard matrix is working perfectly right now. So it's hard to say if the diagnostic was wrong about whether or not they worked or not. It could be that just the joystick ports are broken, which means that most everything in the CIA chip is working. It's just the joystick ports may be not working. Or, and this is the other possibility, is that there's bad contacts. It could be that the joystick ports have bad connections in them or are a little bit too corroded and I need to clean them off. So in a future test, maybe we can do that. Today, though, I am going to see if possibly we can play some music. So let's try that. I have here what's called a Pi 64. Now we'll just see if it can actually read off of this. This is a good test of the I/O port. Oh, that's a good sign. It's definitely trying to load, so that's good. And oh, good. This is good. Just going to put it in the lowercase mode. So why don't we try the classic Donkey Kong Country. So good sign. That means I was able to load up using in order for it to load, it has to use the CIA chip. So that's a good sign. It was able to load. It was able to use all of the keyboard keys, although it seems the keyboard needs a little bit of cleaning. I could probably do that in a different video. It was able to play music. It's using the ARM SID right now, so that means that that's working. I have not tested the joystick ports, but if all of the keyboard's working, it's a good sign and likelihood that the joystick port is likely to work too. Anyway, I will leave it here, and I will consider that a absolute success. Well, that concludes part 1 of the ZIF64 conversion for the Commodore 64. I was already planning to be converting it over to ZIF64 anyway, so that worked out for me. But also, this particular video was focused on just fixing the Commodore 64. The next videos will be looking more towards converting it completely over to the ZIF64, as well as doing some other mods to it as well that are necessary. Looking back at what I've done so far with this ZIF64 that I'm creating, what I completely replaced the PLA chip. Now, in identifying that it was the PLA, I used resources online, which I'll link below, that also identifies the likelihood of what the failure modes could be. So I'll keep those links down there. I'll include those links so that you can fix your own if you want to in the future. There is a lot of help in there for finding it out. If it was a black screen, there's a lot more possibilities of what could go wrong. But because it kept flip-flopping between a black screen and that very strange rolling screen with the borders changing all the time, that was definitely would normally have been an actual PLA failure in most cases. My understanding about the PLA failure is that they added too much boron in the glass layer, more than 4%. And so what happened was it ate through the glass layers and caused a bit of a purple sludge to develop. It was an oxidation that developed between the aluminum and the boron. But if I'm wrong about that, leave your comments down below and let me know what the actual truth is. I know that other people have mentioned that this is what the failure mode is in this particular chip, and in some of the Commodore chips between 1983 and 1984. And I knew that the likelihood of the PLA failure was very high in this particular model. So that's why I went for that first. The fact that it fixed everything right up front is just more luck on my part, actually, which is not really the way you should be working on systems. You should try and debug what the actual source of the problem is first. However, in part 2, we will be looking more deeply at what we can how we can convert this completely over to a ZIF64 and step-by-step replacing each of the chips with ZIF sockets. So I hope to see you on that part next time.